Welcome back, Rust. So, we're diving into web servers today. Let's start with the basics. What are these protocols you mentioned?
Protocols, Matthew, are like the rules of the road for data communication. Think of it like a set of agreed-upon instructions for how information travels between a client, like your browser, and a server.
Okay, and you said HTTP and TCP are key. Can you unpack those?
Absolutely. TCP is the underlying protocol, handling the actual transport of the data. It ensures the data arrives reliably, kind of like a reliable delivery service. HTTP builds on top of that, defining the format of the requests and responses.
So, HTTP uses TCP under the hood? Is that always true?
Almost always. HTTP relies on TCP's reliability. While theoretically possible to use other protocols, it's just not done in practice.
Interesting. So, the server is listening for these requests, and HTTP defines what that request looks like, right?
Exactly. The HTTP request tells the server what resource the client wants, like a specific web page or file.
How about errors? If something goes wrong, how does it signal that back?
Through the HTTP responses. A 200 OK means everything is fine. A 404 not found means the resource wasn't found. Different codes signal different problems.
So, this is kind of like a standard language, right?
Exactly. It's a universal language for web communication, letting all browsers and servers speak the same language.
How does this relate to financial applications, Rust? Say like stock trading?
Well, imagine a trading platform. It would use HTTP requests and responses to send orders to the exchange, retrieve market data, and manage accounts.
So, a stock trade involves these same protocols?
Yes, the protocols are fundamental to modern internet applications, powering everything from web browsing to financial transactions.
What happens when there's a breakdown in the protocol? Say, a glitch in the TCP connection.
The client or the server could potentially lose data or get errors in the response. This is why robust handling of these errors is crucial in any application.
It's like a chain. If one link breaks, the whole process can fail.
Absolutely. This is why fault tolerance is crucial in financial applications, making sure that orders go through correctly despite potential network issues.
It all comes down to reliable communication. Makes sense. Thanks, Rust.
My pleasure, Matthew. We'll explore these concepts in more detail as we build our single-threaded web server in the next segment.
Welcome back to the show, Rust Jackson. Today we're diving deep into TCP connections using Rust. Let's start with the basics. What exactly is a TCP connection?
A TCP connection, Matthew, is like a phone call. You establish a connection, you talk, and then you hang up. It's a reliable, ordered stream of data. Crucially, it guarantees the data arrives in the correct order and ensures all the data arrives.
So, how do we create this connection in Rust?
We use TCP Listener from the standard library. It listens for incoming connections at a specific IP address and port. Think of it as setting up a phone to receive calls.
And the code snippet shows TCP Listener. Bind 127.0.0.1:7878. What's this 127.0.0.1?
That's the local host address. It means the server is listening only to connections on the machine where the code runs, not the internet. The 7878 is a port number, like a telephone extension. Each port has a dedicated number, and that's how our server knows which connection to handle.
Okay, so we're binding to a specific port. What happens if two programs try to bind to the same port?
Then you get an error. The operating system won't allow it. You can't have two people using the same telephone extension at the same time.
So listener data incoming is a big deal. What does that do?
That part is like a call waiting feature. It's an iterator. It keeps waiting for incoming connections, and for every new one it gives you a TCP stream to use.
So, we have a stream of incoming requests, but the code snippet then says .unwrap. What's that all about?
That's a shortcut way to handle errors. It basically says if something goes wrong, stop the program, don't try to handle it gracefully. In real-world applications, we usually do something much more robust, something that says to retry the connection or log the error and keep going.
So, errors are possible? What kind of errors might happen when a client connects?
Well, the incoming connection might not even be successful. The client might not exist, or there might be too many connections already. A lot of times, it depends on operating system limitations. You might get a connection reset error from the client because the connection is temporarily unavailable.
So, if we're handling a stream, we need to know how to read and write data to it. That will be important for processing requests.
Correct. The next step is to work with the TCP streams.
What can we do with this stream?
We can read and write data from it. Right now, we're just printing a message for each incoming connection. That's the first step in a full server.
Got it. So the server will listen for incoming connection attempts. And when a connection is established, it prints a message. This is the foundation of a TCP server in Rust. How is this related to financial applications like online trading platforms?
A real financial application needs a reliable way for many clients to connect and send/receive information. TCP provides that reliability. Imagine high-frequency trading. TCP is fundamental for handling massive volumes of transactions. The server here is handling the socket.
Excellent explanation. So, in essence, the code we saw establishes the foundation for a robust TCP server, which in financial applications could handle a significant amount of incoming requests and data. Thank you, Russ Jackson.
You're welcome, Matthew.
Russ Jackson, welcome back. Let's dive into handling HTTP requests. This chunk introduces reading from the TCP stream. Can you break down how this works in practice?
Sure, Matthew. We're essentially grabbing the data the browser sends. Imagine it like a water hose. The browser is the tap, and the TCP stream is the hose. We need a way to capture that flow of information.
So, how does stream.read and mut_buffer work? What's happening under the hood?
The stream.read function reads data from the stream and puts it into the buffer. It's crucial that buffer is mutable and mut. That's because the stream might have more data than we've requested, and we want to be able to collect that extra data. Think of it like a bucket. We need the bucket to be able to change, fill, and capture all the water.
Why a fixed size buffer? What about larger requests?
Good question. A fixed buffer size, 512 bytes, is simpler to implement, particularly for our current needs. But handling potentially huge requests requires more complex buffer management, which we'll address later. For now, this works well enough.
How does string from _UTF-8_lossy fit into this?
It's like translating the raw bytes from the buffer into something readable. The lossy part is important because sometimes data isn't perfect UTF-8. If it encounters something that's not valid UTF-8, it replaces those problematic characters with a special character called a replacement character. That way we don't crash if, say, some bad data gets into the stream.
So, practically, if I have a web server and someone asks for a file, how would this work in the real world of financial apps?
You'd use this to receive requests like user login credentials, transaction details, or other inputs related to your financial application. It's a crucial step for receiving client requests.
Okay, so we're reading the request, which is great. But what if the buffer isn't large enough for the entire request?
That's a potential problem. Our code might miss a part of the request if the buffer size is too small, and it won't be able to receive the complete request. We'll have to implement a better way to handle requests of varying sizes.
I see. So you're saying we need to look into more advanced methods for handling requests in the future to accommodate larger data sizes, which is also necessary for large financial transactions, right?
Precisely. For now, it's sufficient. Imagine trying to store all of a user's account information, every transaction detail, or anything from a complicated financial system in one 512-byte buffer. It just wouldn't work.
Great insight. How about error handling? What happens if something goes wrong when reading the stream?
The unwrap method is risky. If a read error occurs, the program will panic. In production code, we should use .expect to handle errors in a more robust way, allowing us to identify and deal with potential issues. That is a critical security measure for a financial application.
So, what would a more robust error handling look like in code?
We'd use .expect to provide context or a descriptive message in the case of an error. This is a better approach than simply panicking.
Thanks, Rust. This is very helpful. So, in short, we read the request from the browser using a buffer, convert it to a string, and then print it, all while accounting for possible errors and sizes. How about some practical implications? How could this kind of setup be beneficial for a financial trading system, for instance?
Exactly. It allows you to receive orders, process transactions, and update account information, all data essential for a financial trading platform. The more complex the data, the more important error handling and scalable buffer management becomes. It is also crucial for handling fraud.
Excellent points, Rust. Now, do you have any additional troubleshooting tips if you encounter issues with the request handling process?
Well, if you see weird characters or unexpected behavior, examine the output of the request to ensure it matches the expected format. Verify the connection is intact. Sometimes, network hiccups can also cause issues.
All right, Rust Jackson, let's talk HTTP responses. We're building a web server, and we need to send back data. How do we craft those responses?
Right, Matthew. The response follows a specific format. First, there's a status line.
A status line? Like a status update for the request?
Exactly. It tells the client how the request went. HTTP version, a status code, and a reason phrase.
Okay. And then?
After the status line, headers, then another empty line, and finally the message body. Think of it like an email. Headers give details, and the body contains the actual content.
So, a status code of 200 means success?
That's right. A 200 OK is standard for a successful request. We need to send this data correctly to the client.
Cool. Now, in the code, we have a variable response which is set to the HTTP response. How do we get this data to the client?
We convert the string to bytes using as_bytes. Then we use the write method on the TCP stream to send the bytes down the connection.
So, we're essentially sending the data to the client?
Precisely. It's like writing a letter and putting it in the mailbox. This write is where it gets sent. We need to flush the data.
What does flush do? Why is it important?
Flush ensures all the bytes are sent. If we just write, the data might sit in a buffer. Flush makes sure the client gets the response.
So, this is how we construct and send HTTP responses from our server?
Yes, we craft the response, convert it to bytes, and send it via write. We guarantee transmission via flush. Crucially, we handle potential errors. Error handling is vital.
So, if the write fails, the whole process breaks down?
It does, in theory. But in a real app, you'd wrap the write in error handling, like a match statement. Without that, the whole program crashes.
A real-world example in finance?
Imagine an API sending stock quotes. A 200 response means the quotes were delivered. Any other status code signals an issue, a network problem, data not found, or authentication failure.
A 500 error, for example?
Yes, a 500 server error implies an internal problem on the server.
So, if we made a mistake and omitted the flush step, the response might not get delivered?
Exactly. The data might remain in the buffer. You need that flush to guarantee delivery.
Makes sense. Thanks, Rust. We've covered sending simple HTTP responses. Any final points?
Always remember error handling. In the real world, network problems are common. The code should account for it.
Perfect. We've covered the critical elements of sending HTTP responses. Great work, Rust. All right, Rust Jackson, we're diving into serving HTML now. So, we've got this hello.html file. What's the plan for actually returning that to a user's browser?
We're taking the contents of that file and sending it back as part of the HTTP response. It's a straightforward process, really.
Straightforward? Elaborate. How does the server know what to send back?
Good question. The server's reading the file and then including it in the response. Crucially, it's packaging this with the correct HTTP headers to tell the browser it's HTML.
So, we're building the response from scratch?
Precisely. The code formats a string which includes the HTTP status code, like 200 OK, and then the actual HTML file contents. It's a carefully structured message.
So the code's constructing this message. What does that look like in practice?
The FS, Read underscore string function is crucial here, pulls the data. The format function, on the other hand, takes that file data and adds it as the body of a proper HTTP response.
This is essentially putting the HTML into the response body.
Correct. And importantly, we use the unwrap method, a common practice in Rust, which means we're assuming the file exists and can be read successfully.
But what about error handling? If the file doesn't exist, or it can't be read, what happens then?
Excellent point. The unwrap is a bit dangerous in this situation. Ideally, you'd use a result type to handle potential errors, such as the file not found. Then, you can return an error response code to the client, e.g., 404 not found, instead of crashing.
So robust error handling is critical in real-world scenarios.
Absolutely. Failing to handle potential issues like that can make a big difference when scaling an app.
So, the file is the primary content. But what about other possible requests? What if someone requests /something else instead of /?
Exactly. We are ignoring all other requests currently. This setup only works if the request is to the root of the server.
Right. We need a more sophisticated approach that handles these different requests. What techniques could we implement?
We can use matching or other pattern matching techniques for the requests to handle different routes and requests. This will make our server more dynamic and interactive.
Okay, so we're seeing the groundwork for a more practical web server. What are the practical considerations for handling larger web applications with more complex requests?
It gets significantly more complex. You'd likely need libraries that can handle complex HTTP requests, including routing logic, to serve different pages or resources effectively.
Okay, so we are moving beyond a static response system towards something more dynamic.
Exactly. Building a robust web server requires careful considerations for error handling, routing logic, and handling different types of HTTP requests.
Okay, Russ Jackson, we're diving into handling different HTTP requests. This is crucial for any web server, right?
Absolutely. A web server needs to understand what a client wants and respond accordingly. It's like a waiter at a restaurant. You tell them what you want, and they give you the right dish.
So, in this code, we're checking if the request is for the specific path /. Why is that important?
That's the main entry point, the root of the site. For example, in a bank's online portal, / might be their homepage where people log in.
How does the code know if the path is /?
The code checks if the client request starts with the bytes, get /http/1.1 / It's a specific string that tells the server a standard request.
So, if it doesn't match, what happens?
The server sends a 404 not found error. This is the code's response for paths other than root.
So, how does that work in practice?
The server builds a response string with http/1.1404 not found.
And what does it return if there is a request for /?
It returns the contents of a predefined HTML file named hello.html.
Okay, so we're preventing the server from accidentally giving out sensitive data.
Exactly. You're creating secure and robust interfaces.
And what would the 404 response file look like?
It's just another HTML page to show the user that the requested page isn't available.
This looks like a standard error page.
Precisely.
How does this apply to a financial application like a stock trading platform?
It's crucial. A user request for a non-existent order might trigger this error, protecting from unauthorized access to sensitive financial information.
Okay, so the server now serves different responses based on the request path.
Correct. This code improves the server's response to the user and prevents a potentially unwanted situation from occurring.
So, the user gets a custom error page when they ask for something unavailable.
A well-designed error page can make a significant impact. It shows the user something rather than just a blank screen or an error message.
How can we ensure users don't get the wrong file inadvertently if the file name is similar?
You can use pattern matching or regular expressions to be extra cautious.
Sounds good. That clears up a lot. Thanks, Russ Jackson.
You're welcome, Matthew. Glad to help.
Great. Let's move on to the next section. Okay, Russ Jackson, let's dive into this refactoring. You're saying we can make this code more compact and readable?
Yeah, Matthew, we're improving the structure. The if and else blocks were doing the same thing, basically reading a file and writing to the stream, but with different status lines and file names. We pull out those differences into variables.
So, like extracting the differing parts of the condition? That makes sense.
Exactly. Now we've got a single consistent block for reading and writing, with the if and else determining the actual values assigned.
So, the repeated code is removed, right?
That's correct. It's organized better because we move repetitive parts outside the if/else block. It's more straightforward when you want to change how the response is handled.
How does this help with scaling? Or maybe even for something more financial?
Well, in a financial app, imagine handling different types of transactions. Each transaction type might require unique responses. This refactoring would help you code that in a more organized, scalable way.
Okay, that makes sense. How about a troubleshooting scenario? What if a file can't be found?
If the file doesn't exist, you'd need to handle that appropriately. Maybe, in a production application, log the error and send a more informative 404 error response.
So, that's a key takeaway. Handling potential errors is critical in any application.
Absolutely. Robust error handling is a huge part of production code. Otherwise, unexpected conditions can crash things.
So, this refactoring makes our server cleaner and potentially more robust in case of issues with the files. Cool.
Exactly. This refactoring will be critical for scaling our server. We'll be able to understand and maintain the code base much more easily.
What about the performance aspect? Is there an actual speed up in the way that the server handles the request?
Not directly from this refactoring, no. This is primarily about code clarity and organization. The performance improvement would come with the next steps of adding concurrency, which we'll discuss shortly.
You mean making the server handle multiple requests at once?
Exactly. This current version is single-threaded. So, handling the next request will start after finishing the previous one.
So, a slow request will block the server from responding to others?
Absolutely. That's a significant limitation for a web server. We need to fix that to handle concurrent requests effectively.
Makes sense. This is all really helpful, Russ Jackson.
Thanks, Matthew.
Russ Jackson, welcome back to the show. Today we're diving into thread pools. Can you give us a high-level overview?
Sure, Matthew. A thread pool is basically a team of worker threads, ready and waiting for tasks. Imagine a factory assembly line.
Okay, a factory line. So, each thread is a worker?
Exactly. When a new task arrives, like a customer order, one worker picks it up and gets to work processing it. The other workers are just waiting for more tasks.
So, it's like a queue system?
Sort of. It handles tasks concurrently, meaning multiple things happen at the same time. This boosts throughput, like speeding up production.
How does it prevent things from crashing?
Well, we limit the number of workers. It's like a factory. You don't want too many workers or everything gets messed up. If too many requests come in, the workers queue them up, and that's important for handling high traffic.
So, the workers handle the tasks one at a time in the queue?
Precisely. One worker grabs a task, processes it, and then goes back to the queue for another one. This is great for handling many simultaneous requests.
What about long-running tasks?
If you have a bunch of long-running tasks, subsequent requests could still pile up in the queue. But you can manage a lot more long-running requests at once, versus one big request at a time.
So, it's about managing the resources to avoid server overload, like a DOS attack?
Exactly. We're limiting the number of simultaneous workers to make sure your server doesn't get overwhelmed.
Interesting. What's the connection to financial applications?
Imagine high-frequency trading. You need to process tons of orders very quickly. A thread pool is perfect for that, handling many transactions efficiently.
So, what's the best way to design this kind of code?
It's a good idea to define the API first, like a blueprint for what the functions will do. The client interface is crucial for this. Write the client interface first and implement it.
A bit like test-driven development. Using the compiler as our guide?
Absolutely. We write the client code calling functions. Then, we use compiler error messages to improve the implementation. It's a useful feedback loop.
So, a thread pool handles concurrent tasks and protects against server overload.
Correct. It's a crucial technique for boosting throughput, particularly in high-demand situations. It's all about resource management.
Thanks, Russ Jackson. Very helpful insights into thread pools. This is excellent information for our listeners. Russ Jackson, welcome back to the show. Today, we're diving into thread pools in Rust. You've been talking about making this easier to use, right?
Yeah, Matthew. We want to create a user-friendly interface for thread pools, similar to thread spawn. Imagine a function that lets you easily hand off work to a pool of threads.
Sounds great. What's the basic idea? What are the benefits of using thread pools instead of just spawning threads directly?
Well, thread pools manage a group of threads. You can get better performance by reusing existing threads instead of constantly creating and destroying them. Think of it like a server with many customer service representatives. You don't want to hire a new rep every time a customer calls, right?
Right, that makes sense. You're saying it's more efficient. How does this thread pool structure work in practice?
This thread pool lets you create a pool of workers. Each worker is ready and waiting to run a task. Then, you pass a task to the pool, and it gets assigned to a worker.
So, you're basically queuing up tasks for execution? Could you elaborate on the function pool.execute?
Exactly. Pool.execute takes a closure as input. The closure is a bit of code that will run on a worker thread from the pool.
Makes sense. But how does the pool know which worker to use? Is it FIFO?
It could use a queue, or other ways to assign tasks. Usually, the way tasks are dispatched among workers depends on the implementation.
Interesting. What does this look like in practice for a financial app?
Imagine a trading platform. You could use a thread pool to handle multiple incoming orders. Each order's processing could be a closure. A big improvement.
Excellent. So, a thread pool is more efficient for handling multiple tasks. So, how are thread pools different from other concurrency models?
Other models, like actors, handle concurrency differently. Thread pools are good for work that can be easily broken down into independent tasks. Actors are better for tasks that need to communicate with each other.
That's clear. A lot to think about. So, this pool.execute function, how does it interact with the worker threads in the pool?
The thread pool manages the dispatch to the available workers. It's hidden from the user how this happens, but it likely uses a queue, prioritizing jobs.
Okay, so you give it a task, it fits it into the pool of workers. What happens if there are no available threads in the pool?
If there aren't any available workers, then you'd have to use queuing mechanisms. The new task would get added to the queue.
That's important to know. What if something goes wrong inside a closure that's passed to pool.execute? What are the consequences?
Errors within a closure can be handled differently depending on the specific implementation of pool.execute and the design of the program. The thread pool, in general, may need to provide some mechanism to signal the error, or handle it internally. Handling errors gracefully is key.
Great points. So, for financial applications, thread pools could significantly improve the responsiveness and performance of systems handling many tasks.
Precisely, Matthew. They're very useful tools in high-performance situations.
Fantastic. Rust Jackson. We've covered thread pools and Rust. Thanks for joining us. Hey, Russ Jackson. Welcome back to the show. Today we're diving into thread pools and Rust. Let's talk about the new function in the thread pool.
Hey, Matthew. Glad to be here. So, the new function, initially, just took a size parameter. But there's a hidden trap here.
A trap? What kind of trap?
Well, if you pass in 0 for the number of threads, that's not a useful thread pool, right? It's nonsensical. But usize can hold 0.
Right. So, what's the solution?
We're adding a check. We're using the assert macro to guarantee that the size is greater than 0.
So, assert size 0. That's a pretty straightforward check. But what happens if that assertion fails?
The program panics. It's a way to say, hey, this input is invalid. I can't proceed.
Okay, so that's a pretty crucial step in robustness. Why not use a result type instead?
Well, we decided that trying to create a thread pool with 0 threads is a fundamental error. It's not something we can recover from. Using result would require handling this error, and the function call would be more complicated.
So, using assert for a fundamental error like this makes more sense.
Absolutely. It clearly communicates that this situation isn't recoverable. It's a design decision to favor explicitness and robustness over possible handling code.
That makes a lot of sense from the perspective of the API caller. It communicates what's expected.
It's about error prevention, and in this case, the assertion is the best way to deal with it.
So, a zero-size thread pool is a design decision?
Exactly. We need to ensure a valid pool size.
So, now it's clearer why assert is used instead of a result.
You bet. It keeps the code clean and focused on the intended functionality. We want to be able to create a valid pool quickly and not get bogged down with error handling.
Let's say a developer is creating a system with a lot of dependencies. Would assert be an effective solution for validating these dependencies?
Not necessarily. If there are recoverable errors with the dependencies, result would be preferable. Assert is designed for things that shouldn't happen in typical program execution.
Great point. You know this detail. Is it possible the program will return without errors if the assert failed?
No, if assert fails, the program panics immediately. This stops any further operations, which is critical for the integrity of the application.
Thanks for clarifying the important distinction between assert and result.
You're welcome. We'll definitely be talking about error handling and validation techniques in future podcasts. It's a complex topic with a lot to discuss.
We definitely will. Thanks for your insights, Russ Jackson. Russ Jackson, welcome back to the show. We're diving deeper into thread pools in Rust. This chunk talks about actually storing these threads. Can you break down how we store threads in this context?
Sure, Matthew. We're building a thread pool struct. Storing threads involves a key concept, using thread, join handle. It's like a ticket to get the result of the thread's work back, so we need a way to associate threads with their results.
So, join handle acts as a handle for a spawned thread. Makes sense. But how does that work in practice?
Think of join handle as a placeholder for the thread's eventual return value. Crucially, it allows us to track the thread and potentially retrieve its outcome later. In our case, the closures passed to the pool won't return a specific value, so the type T in join handle will be the unit type.
So we're essentially storing these join handle objects to keep track of the threads?
Exactly. We're using a vector to hold these join handle objects. This is a crucial step in managing concurrent operations.
A vector? Why not a hash map or something else?
Well, in this case, a vector is simpler and efficient for storing threads, since order isn't important. We know exactly how many threads to create.
Okay, so you have vec. What about vec? With underscore capacity. Why use it instead of a simple vec? New.
Vec, with underscore capacity pre-allocates space for the vector. If you use just vec, new, the vector dynamically grows as you add elements, which can lead to extra allocations and slow down performance in this case. Knowing the size beforehand gives us a performance edge.
So, pre-allocating avoids extra steps in the memory management process?
Exactly. It's like reserving a specific amount of space in your warehouse for your incoming products. You don't have to constantly adjust the layout. Much more efficient, especially for larger thread pools.
This is neat. Let's talk about error handling. What happens if the size is 0 or negative?
The code uses an assert statement. This is a compile time check. It ensures that the size is valid, greater than 0. If it isn't, the code won't even compile, which is much better than runtime errors.
A very robust approach. So, the initial setup of the thread pool involves these crucial steps. Defining thread pool to hold the join handle objects, using vec, with underscore capacity for efficient pre-allocation, and verifying the thread pool size.
Precisely. These are fundamental building blocks when designing thread pools. We need a proper structure and efficient memory management.
You've effectively illustrated how to create the structure and ensure the capacity for our threads. This is a great step. Great explanation, Russ Jackson. Let's keep digging into the thread pool implementation.
Thank you, Matthew. Let's move on.
Russ Jackson, welcome back to the show. We're diving deep into thread pools today. Let's talk about this job type alias. What's the key takeaway?
Okay, Matthew. The job type alias is a shorthand for a box containing a closure that can be executed asynchronously. Think of it as a container holding a function that can run on a separate thread.
So, it's basically a wrapper around a function?
Exactly. And critically, this closure needs to be sendable, send, and statically known at compile time, static. This ensures safety.
Why this structure, though? What's the financial application here?
Imagine a high-frequency trading platform. You need to process many market data feeds concurrently. The job type enables efficient handling of those requests, preventing potential bottlenecks that could delay trades.
Right. Now, let's look at worker. New. What's the deal with locking the receiver?
We use a mutex to protect the receiver. Imagine multiple workers trying to grab a job at the same time. The mutex acts as a lock, allowing only one worker to access the receiver at a time.
So, that's the concurrent aspect? But why unwrap?
Unwrap is a bit risky, you know. It immediately panics on failure. However, in this scenario, we intentionally avoid deadlock or race conditions by checking for errors.
Got it. The error handling is a trade-off.
Precisely. We could replace unwrap with expect to provide better error messages, but this assumes that the channel won't fail.
What about the FN box trait? That sounds tricky.
Right. The FN box trait is a clever workaround. We need a way to move the closure out of the box when we want to execute it, and that's where call_box comes in. It allows Rust to take ownership of the closure.
So, the box wasn't the problem initially?
It was the inability of the compiler to move the closure out of the box automatically when called. FNBox fixes that by giving us explicit ownership transfer.
So, FNbox allows us to avoid issues with the closure's ownership in the context of the box?
Exactly. It's a neat trick to get around limitations with the box and FN once combination.
Why not while letting the worker loop? What's the problem there?
The mutex lock is held for the entire while let loop. This prevents other workers from grabbing jobs until the current job finishes. The loop approach releases the lock in the middle, which is critical for concurrent operation.
So, loop is absolutely crucial for concurrency here?
Absolutely. This design ensures that workers can continually grab new jobs without blocking each other.
So, the financial application of this concurrent processing is very important for things like high-frequency trading, where speed is a major concern.
Exactly, and the FNbox trick allows us to maintain efficiency and prevent delays in processing market data.
Excellent explanation, Rust Jackson. That was a great deep dive into thread pools and closures in Rust.
Thanks, Matthew. It's a fascinating interplay of design choices to enable efficient concurrent execution.
All right, Rust Jackson, graceful shutdown. Sounds important. Why is it necessary?
Yeah, crucial. Imagine a server handling tons of requests. If it just abruptly shuts down, some requests might get lost, or worse, corrupted data could be written.
So, we need a way to tell the threads they should stop?
Exactly. And using Control-C isn't graceful. It forces a hard stop, halting all active threads mid-task.
So, the drop trait. What's its role here?
Drop allows us to define what happens when an object is about to be deallocated, like when the server closes. We can call join on the threads, ensuring they finish their current tasks.
Okay, and this join. Explaining that would help.
It waits for each thread to complete before moving on. Without it, the server could shut down while threads are still working.
Makes sense. So, we don't want to abruptly halt things?
Exactly. We want to wait for them to finish, then clean things up nicely. This is much better practice, especially in the long run. Think of it like winding down before turning off your computer. You're not just turning off the power, you're saving any work in progress.
Cool. And how do we tell threads to stop accepting new requests?
We'd need to introduce a way for the threads to monitor some flag or signal that tells them to stop working. It is important to avoid race conditions here.
So we're not just stopping threads, but managing the flow of new tasks.
Exactly. We'd potentially use a mutex or a condition variable to keep the thread pool aware of the shutdown request and avoid potential data corruption. This ensures that a thread won't accept a new task when the server is shutting down.
2 requests before shutting down. Interesting. Why that specific number?
It's a practical limit. We might want to handle 2 requests, for example, in a queue, and then do the cleanup. It's all about balancing resource usage and responsiveness. Too few requests, and the server might not get many transactions completed before closing. Too many, and the server stays up longer than necessary.
So, you're suggesting a threshold for handling a finite amount of requests before doing a graceful shutdown.
Yes. It's like an explicit queue size limit. A queue would get full and the system would stop accepting more requests until the queued requests are processed. You can vary the threshold based on server load and desired response time. If we just blindly waited forever, that wouldn't be great.
Okay, so we're setting a limit on the queue. Then when the queue fills up, we signal for a graceful shutdown of the thread pool.
Exactly. It prevents the server from becoming unresponsive or having lots of pending requests hanging around. It's good design for maintainability and resilience.
Thanks for explaining graceful shutdown, Rust. It really helps to see it in a practical context. Russ Jackson, welcome back to the show. Today, we're diving deep into graceful shutdowns in Rust web servers, leveraging thread pools. Let's start with the fundamental problem. Why is a simple join not sufficient for shutting down threads in this context?
Well, Matthew, the join method in a thread pool essentially waits for the thread to finish its current task. But in our case, these threads are running in an infinite loop, constantly checking for new jobs. If we just join, without any way to signal the loop to stop, the main thread will wait forever.
So, a signal is needed to tell the thread loop to exit. How does this signaling work in the code?
We introduce a message enum with 2 variants: new job, holding the job, and terminate. This allows the threads to react to either a new task or a shutdown command. Critically, we modify the channel to use this message type instead of just the job type.
Okay, so the message enum acts as a communication channel. How is this used within the worker struct?
The worker now continuously receives message S from the channel. If it receives a new job, it executes the contain function. If it gets a terminate, the loop breaks. The clever part is that the threads are now able to exit cleanly when the signal arrives.
The code also mentions iterating over workers twice. Can you clarify why 2 loops are necessary?
Imagine 2 workers, Matthew. If we did it in one loop, the second worker might get the shutdown signal, exit, and the main thread waits for the first worker. This first worker might not have received the shutdown signal. So we prevent this potential deadlock. We send all the signals first, and only then do we wait for them to finish.
Gotcha. So we first send a shutdown signal to everyone, then wait for the threads to close. What about the drop implementation?
Precisely. The drop implementation for the thread pool sends a terminate message to all workers, ensuring each thread gets the signal to exit. This is crucial for graceful shutdown.
A real web server wouldn't stop after 2 requests, though. Why is the code in main designed that way?
This is a simplified example, Matthew. It focuses on the correct graceful shutdown procedure. This demo showcases the mechanism without unnecessary complexity.
You mentioned take 2 in the main function. Could you explain what take 2 does?
Take 2 is an iterator method. It limits the number of items you can iterate over to the first 2, which makes the demo clear and fast.
What would be the next steps to enhance this project?
We could add documentation to the thread pool methods, write tests to ensure our functionality, handle potential errors more robustly, and explore using the thread pool to handle other tasks beyond web requests.
Great insights, Russ Jackson. This graceful shutdown mechanism is critical for robustness in concurrent applications. Thanks for explaining this.